In this video, we are going to learn about our second involved or heuristic search called greedy best first search. So how this greedy best first search algorithm works? This algorithm seeks to minimize the estimated cost to the goal by expanding the node estimated to be closest to the goal state. In this case, this algorithm will always expand the heuristically best nodes first. Let's see the preview of the algorithm of greedy best first search. In the greedy best first search, we will use a queue data structure but only containing the root, the queue. And then we will do looping. While the queue is not empty and the goal is not reached, we will do the following. We will remove the first path from the queue and then we will create a new path to all children. Next, we will reject all new paths that will create loops. Then we will add the new path and sort the entire queue. If the goal is reached, then success. If the goal is not reached, then it means failure. So there is a possibility for this greedy best first search to not find the expected solution. So let's see here that we use queue. The queue that we use is equal with our open list. Let's see an example of how to use this greedy best first search algorithm. Let's say that we have this case, the traveling postman from Romania. This is a map of Romania. There is a postman that is required to send a mail or to send a post between each city in Romania. Each city in Romania is depicted in this map with the number is the step cost in kilometer. The heuristic that we will use will be the straight line distance city of N. City N is our current city to our goal state. So this is the heuristics that we will use later on. Refer to this list. For example here, from the city of Serin to, let's say our goal is Bucharest, then the heuristic will be from Serin, this one, to Bucharest, straight line distance to Bucharest will be 374. And the number above the line or next beside the line shows the distance between two connecting cities. Okay, let's see another example of the heuristic. In here, from Timisoara, we can just take on the straight line from Timisoara to Bucharest and the value would be 329. Let's use this map and solve it using greedy best first search. Let's say we want to find the distance and then the traveling path from Arad to Bucharest. In here, we know that Arad, this one, the heuristic from Arad to Bucharest will be 366. So we will put Arad and 366. 366, this is the heuristic from Arad to Bucharest. This is our open list. The queue, and then we have our initial closed list will be empty. Next, we will see, based on the map, the immediate city that is connected with Arad will be Serin, CPU, and Timisoara. So, we will remove Arad from our open list and move it to our closed list. So, it will be like this one. From Arad, we can go to CPU, Timisoara, and Serin. And we will add Arad to CPU. We will add CPU, this 253, again, this is the heuristic value from CPU to Bucharest. Let's see. From CPU to Bucharest, the straight line, CPU to Bucharest is 253. So that's why we have it here 253. Timisoara. The heuristic value from Timisoara to Bucharest will be 329. So remember, this is shows the heuristic value, not the distance between Arad, Timisoara, Arad CPU, and Arad Serin. We have moved Arad to our closed list. We expand all the child nodes here. We have each child node with its own heuristic value. Next, what we want to do will be, we want to sort these three child nodes and find out sort in the ascending order. The smaller one will be located at the front of our queue. So in this case, we'll get CPU, which has the smallest value, located at position at the front of the queue. So next, we will explore CPU. CPU will be our next city, this one. So from CPU, when we expand CPU, there are three other cities that we can visit, such as Făgăraș, Oradea, and Râmnicu, Visea. We put Făgăraș, Râmnicu, Visea, Oradea into our queue. These three numbers are the heuristic. Once we get Baccarat, Oratea, Rymnicu, but remember, since previously we also have Timisoara and Serin in our list, so don't remove Timisoara and Serin at this moment. We will repeat the algorithm of base first search. So after we put all the child nodes into our open queue, then we will sort. Once we sort it, we will get that sequence will be Baccarat. It has the smallest heuristic value. Next will be Rymnicu. This is position 1, this is position 2. Next, we will have Timisoara, Serin, and finally we have Oratea. So this shows the queue after the sorting process. Baccarat, Rymnicu, Timisoara, Serin, and Oratea. Next, since our goal state will be to Bucharest and we must explore Baccarat, we move Baccarat to our close list, and now we see that Baccarat has the immediate connection to Bucharest. So we put Bucharest in our open list or in front of our queue. Then since Bucharest is also our goal, then we have already generated our goal. The path will be from Arad, we go to CPU, from CPU we go to Baccarat, and then we will reach Bucharest. Let's see another example. If we want to go to Bucharest from Dobreta, find out the path. This is the heuristic value of Dobreta to Bucharest. We write it down in our open list or in queue. Then we will move Dobreta to our closed list. Then we'll know Dobreta, it actually has two immediate city, which is Craiova and Mehadia. So once we move Dobreta from open list to our closed list, then we get Craiova and Mehadia. So we sort the queue, we put Craiova in front of our open list. So next we will expand the Craiova. So from Craiova we know that it has two child nodes, Pitesti and Rymnicu. We move Craiova to our closed list. So we get Pitesti, Rymnicu, and Mehadia in our open list. And this is the condition of the list after it has been sorted. Next, after we choose Pitesti, Pitesti has immediate connections to Bucharest. So we will move Pitesti over to the closed list, and then Bucharest enters the open list, and then sort it out. And we already get this Bucharest in front of our open list. So we have found the goal. In this case, since we have already found the goal, then the path, we know the path from Dobreta to Bucharest will be Dobreta to Craiova, then to Pitesti, and then to Bucharest. Let's see some of the properties of greedy search. First of all, greedy search is not complete. It is not a complete algorithm. By using greedy search, it's very possible for our algorithm to get stuck in a loop. Greedy search can be said complete if search space is finite and there are checking process for repeated states. Secondly, greedy search itself is still not an optimal algorithm. It has a time complexity of big O, p exponent to m, where p is the number of branching vector and m is the maximum depth of the search space. So if you have limitations on the depth of the search space, then again, it may lead to an incomplete search tree. So in this case, greedy base first search, it has the same worst case time complexity as depth first algorithm. This is from the time complexity. Let's see the other complexity that is generated by this greedy base first search, which is the space complexity would be, the big O will be the p exponent by m. Since greedy search will keep all the nodes in its memory, so it is worse than the big O of Pm, which is the worst case space complexity for the depth first search algorithm. We can say that the actual performance of greedy base first search will be heavily reliant on the accuracy of the heuristic. Any questions so far? If you guys have any questions, you can write it down on the comments, or you can send an email, or you can send it to the class group space. Thank you. For this week, we have two simple exercises. The first, please create the illustrations to search for the best route using greedy base first search algorithm, as in slide 20 to slide 27, where you need to traverse the routes from Serin to Bucharest. Create the illustrations to search for the best route using greedy base first search algorithm. The start state will be Serin. The final state will be Bucharest. Again, this exercise must be in handwritten. Submit it, on the online platform on the ULS. And as an additional notes, we also have additional announcements. This one next week, week 4 is actually the quiz schedule. We will have no offline classes in week 4. The quiz will be held online through the ULS platform on Friday, 24 March 2023. So next Friday will be the online quiz. The quiz link will be open from 3:45 to 6, and the time to do the quiz is 100 minutes. So you are free to choose when you want to do the quiz. However, please remember that there is a time limit. You are only limited with the 100 minutes to do the quiz. Therefore, don't start the quiz after 4:20 because you will have less than 100 minutes. Okay, so if you guys don't have any questions, see you again next week.